Okay, well, thank you very much. What a pleasure to be here. I've been very excited to hear everyone's thoughts and ideas over the morning and into this afternoon. I have to say, following Pete is a little intimidating, especially talking about Starshot. But actually, by the time I get to my last slide, I'll circle back around to this question of interstellar exploration. So what I thought I would do very briefly is a bit of science, or at least throw a bunch of science ideas out there that are related to astrobiology, which I think lends itself extremely well to what we're talking about here in terms of space exploration and in particular private space initiatives. So I'll talk about astrobiology and then I'll throw some ideas at you, which will be increasingly crazy. So astrobiology, it's the science of life in the universe. And it really comes down to a couple of big questions that define this science. And the first of those big questions is a simple sounding one: are we alone? And that is an ancient question, but today we're pursuing that question, and it's the sort of royal we. I don't mean, oh, humans alone. It has something like this: life on Earth happened anywhere else in the universe. And what we know today is that if we could find just one other example of life, an independent abiogenesis somewhere else in the universe, it actually would give us vastly improved quantitative constraints on the cosmic probability of life. It would in effect tell us that there is life everywhere in the universe. So that's just part of the motivation for modern astrobiology. Just finding that other instance of life that happened and evolved independently of life here. And it could be in the solar system, it could be somewhere else. The second big question is, how does life originate? Where does life come from? What are the processes that give rise to life? What are the pathways? How do we have chemical complexification in the right sort of environment out in the cosmos to make life happen? These are the central questions for astrobiology. But they naturally lead to a whole bunch of other questions, and I could put many more up here, but I'll just put two on this introductory slide. Follow-on questions that I think are kind of at the forefront of current research are, for example, to do with understanding the way in which life is integrated with the environment that it exists in particular planetary environments. As far as we know, life is a planet, or maybe it's a moon type thing. It's a phenomena that happens on these large-scale environments. And so the planet life question is really at the forefront. And today, we tend to say less that planets like the Earth produce life, or life comes from planets, or whatever other environment, more that life happens to a place. It happens to a planet. It's an infection. It's a catalytic infection. It's a thing that just alters the fundamental nature of a planet. And the Earth has been changed constantly by life over the last 4 billion years in a great network of feedback loops. There are other questions that come up when you start to think about life in the universe. For example, existential threats to living systems. Okay, now this is something that's boiling around in our minds, especially after this week with certain decisions made at a high level. But existential threats come in different forms. There are simple existential threats. An asteroid is a simple existential threat, or a supernova. More complex things like climate systems and questions about the long-term trajectory of living systems in space and time are also part of astrobiology. Because it's not just about learning whether or not there's other life out there, it's putting ourselves into context, our past, our present, and our future. So, I realize I don't have too much time here, so what I'll do is get to the question of exploration and experimentation in space, and I'm going to throw out a bunch of ideas here that are going to be sensible to speculative. So let me start pretty sensible. I think we've heard a little bit about exoplanets already. We just heard about Proxima Centauri b, for example. I wanted to say that exoplanetary science is a really hot area. It didn't exist before the early 1990s, and as I'm sure you're aware, we've now discovered literally thousands of planets around other stars, and we are beginning to get to the point we're on the cusp of being able to make more quantitative statements about the nature of some of those planets, their compositions, their characteristics, and so on. And a lot of that science, in fact, the majority of that science has been supported by states, by federal funding, and we talk about giant telescopes. Well, giant telescopes are always good. Right? If you want to build me a giant telescope, wonderful, thank you. But there's a lot you can do with small telescopes, especially in space. The space environment is really good for astronomy. It offers stability. It offers you an absence of an atmosphere to have to stare through, and all sorts of other good things. So there are lots of things you could do with small telescopes. You could, for example, and these are just crude examples, have small telescopes out there monitoring stars, looking for exoplanetary transits. That's when a planet makes a tiny eclipse in front of its parent star, performing ultra-high precision photometry and timing. These could be small things. They could be like a box like this, sitting out in space. Space-based proxy science. This is something that's been bubbling around for a while, and I think there's a lot of opportunity here because there are a lot of potential surprises. Because we've never actually seen an exoplanet up close, we're basing most of what we do on extrapolations from our own solar system. And we could use Earth, Mars, Venus, and other objects in our solar system as proxies for some of the exoplanets. In fact, recently there was a beautiful piece of work done using data from this Discover satellite that saw ice glint due to horizontally aligned ice crystals in high clouds above continental landmasses on the Earth. And that ice glint is something you might be able to spot on Earth analog exoplanets. Well, we didn't know it would be there. We didn't know it was a phenomena that existed until this observation was made of the Earth. And seeing that ice glint gives you all sorts of insight as to what's going on a planetary system. I have to throw this up. This is a kind of a pet thing of mine, but it's kind of interesting. And I'm trying to be a little provocative here, so please don't analyze that. Don't peer review the science I'm showing you today. Can small telescopes image other planetary systems? That's kind of a holy grail, is getting an image of a planetary system, either of little dots of light circling the star or trying to do a little bit better. Well, it's really, really difficult. But part of the difficulty is that we've focused on certain wavelengths of light. In fact, you could do it if you go to the extreme ultraviolet. If you shrink the wavelength of the light that you're looking at, your optics, just as basic optics 101, your diffraction limit goes down and down and down. So in fact, something of the order of a 1 meter class extreme ultraviolet diffraction limited telescope, which can be built using special multi-layer optics, could image stellar disks of nearby stars. And that means you might be able to even image a planetary transit. I mean, this is just a cartoon. This is not, this is just me taking a picture of the sun and putting a black dot on it. But you might actually be able to see something akin to this watching a planetary transit directly. But you could also potentially probe the reaction of planets that have magnetic fields and atmospheres to things like stellar flares. You might see auroral responses on planets due to stellar flares. And that means you're actually probing the geodynamo of planets. You're probing the interior of exoplanets with a telescope that's maybe about 1 meter across. So do that, okay? Okay, so now come back to the solar system a little bit. I just wanted to say this because I hadn't quite heard it articulated yet today. The solar system has a lot of real estate. Okay, it's a big place. There are known 8 major planets, 178 natural satellites, 3,469 cataloged comets, 733,034 cataloged asteroids at this moment. That is an awful lot of places to go and look at, and most of it we have never seen up close. There's a great terrain to explore. But part of that terrain is actually right on our doorstep, and I wanted to say something about that. And now I'm starting to move into the crazier stuff, but this is actually not so crazy. An out-of-the-box exploration idea. So the moon is a cosmic garbage dump. Okay? Basically, all the crap that's happened to the Earth in the last 4 billion years, to some extent, there's a record of that on the moon. And I say that because basically every time the Earth has been hit by a major asteroid in the last 4 billion years, there will have been ejected pieces of the surface of the Earth, lithospheric material. Some of that will absolutely have ended up on the lunar surface. The moon does not have an atmosphere. It is weathered by meteorites and micrometeorites, but that's slightly different. It's a different sort of weathering. So in principle, there's a record of a lot of major events that have happened to the Earth in the last 4 billion years of astrobiological interest. It has also recently been pointed out in a very nice piece of work that the Earth's atmosphere ends up getting channeled onto the surface of the moon, and the atoms get implanted in the lunar surface because of the solar wind and the Earth's magnetic field. The outer atmosphere is constantly getting stripped away, and every time the moon happens to pass through that particular region where these atoms are streaming away from the Earth, it gets those atoms implanted on its surface, including biogenic oxygen. So in principle, there is a record of the past 4 billion years, including the rise of oxygen on the Earth. You might be able to distinguish it using isotopic measurements. It's all dumped onto the surface of the moon. So the moon would be a wonderful place to send lots of little autonomous geologists or prospectors to go and sift through the filth to find out about our own deep history and to further our knowledge of Earth-type planets in general. I have to throw this up because this is something Zabi and I talked about at some point, another crazy idea. Well, it's an idea from Zabi, so, you know, it's brilliant and crazy and wonderful. And so there is an old question about whether or not viable biological material can be exchanged between planets in our solar system. How does that work? Well, an asteroid, let's say, hits the Earth, stuff gets ejected into space. It could conceivably carry viable biological material organisms to, say, Mars. Now, we know it happens in the reverse. We know material from Mars ends up on the Earth. We can find Martian meteorites. We don't know whether organisms or biological material can be transported successfully this way. But in astrobiology, it's a quite pressing question because there is some evidence to suggest that 4 billion years ago, the conditions on Mars, the chemical and geophysical conditions on Mars, were more conducive to the type of chemistry that we think was involved or could have been involved in the origins of life. Some people would say life probably started on Mars and ended up on the Earth. That could have gone the other way too. But we don't know if any of that is even plausible. People have done little experiments to try to probe this. So what about an end-to-end experiment? You know, mimicking. You know, we're not going to crash an asteroid into the Earth, right? But we can mimic aspects of what would happen to material in terms of pressure and shock before it's ejected into space. We could then just stick it on a little spacecraft, take it to Mars, pretend it's a piece of ejected material carrying organisms, and then see what happens at the other end. That runs into all sorts of planetary protection issues, but hey, whatever. You know, nature may have been doing this for eons. And that actually relates to the next piece here, which is this idea of extreme isolation experiments. It's an interesting fact that here on the Earth, we may have never seen a truly abiotic natural environment. Biology is filthy. Okay, in this room, floating in the air, are pieces of DNA that don't even belong to anyone in this room. It belongs to the last semester of students who sat in this room every day. Earth is totally contaminated by living things. And that's interesting for all sorts of reasons. One reason is, well, what happens when organisms find themselves in a truly abiotic natural environment? What are they going to do? Well, they're going to be stressed, right? And they're going to respond to that stress by changing things like gene expression. So I think there's a really interesting area of space epigenetics that could be looked at. And people obviously already do this to some extent. The astronaut twin experiment is a great example of that. I was actually just the other night at the World Science Festival talking to someone who works on that. But there are so many other questions we could begin to ask, both about human biology, but also about broader questions of life's survivability in different environments, taking it all the way down to a genetic level. Okay, now I'm gonna get mad. Okay, all right, so people do still talk about stuff like CETA, the search for extraterrestrial artifacts. Okay, now this, I will excuse myself in a moment about why I'm putting this up here. So the idea is, well, humans haven't been around that long. The solar system has been around a long time. We don't know whether or not there's stuff kicking around that is evidence of some technological life that passed through at some point. Now, at this point, you're wondering whether I live in a trailer in Nevada and see things at night. But the reason I put this up here is there is something very valuable in the idea of looking for weird stuff. And it's not to do necessarily with looking for signs of past technology from alien civilizations. Because when you purposefully cast a wide net and keep your eyes open and look for anomalies, look for outliers, you find interesting stuff as a side effect. This image on the left here, that's an image looking on Mars. Now, it's been color enhanced, but there are these weird markings. What are those? Well, those weird markings turn out to be the trails left by dust devils on Mars. Mars is infested by dust devils, and dust devils on Mars actually play an incredibly important role in the redistribution of surface dust to different parts of the Martian geography, and also the atmospheric load of dust in the atmosphere, which is relevant for Martian climate. And people have learned a huge amount by looking at these weird markings on Mars. Another really terrific example is the tentative, putative proposition that there's a giant planet 9 in the outer solar system, and possibly 10 Earth mass planet in the outer part of the solar system, on the outer part of the Kuiper belt. And the data that is pointing towards that possibility comes from looking at extreme Kuiper belt objects and their weird orbital arrangements. And this data has been around for a while, but it's really only the last couple of years people have looked at this and gone, wait a minute, this is strange. All these orbits are tilted in one particular direction, and a plausible explanation is another planet out there. So looking for weird stuff is a wide open arena, I think, and our solar system is big. Okay, last slide. I had to circle back around. I don't want to be outdone by Pete and his $100 million. Other challenges with astrobiological implications along the lines of true interstellar exploration. Well, there's a lot of stuff you're going to do beforehand. And I really, really hope that Starshot makes great progress, because I think it's incredibly exciting. But pre-interstellar exploration, well, solar system tests, we heard a little bit about that just now, and there are a couple of questions about it. Laser signaling, that's very interesting from a technological point of view. An idea that came to me last night, and now I'm really excited about it, so I probably shouldn't share it with you, because maybe it's actually interesting, is the idea, if you build a honking big laser array on the Earth, you could do LiDAR of the solar system, right? Want to understand some object you haven't really seen very well out in the solar system, shine a big laser on it, right? And then get the reflection. We do this with radar, with planetary radar measurements of Venus and even Titan we can do from the Earth. If you've got a big laser, you could do this for all sorts of stuff. You could light up the solar system as you want it and start to explore the solar system without even leaving the surface of the planet. But you do it as a side effect of building that wonderful laser array for accelerating spacecraft. There's Kuiper belt exploration, okay, there's the Planet 9 mystery, but then also the fact that in the outer solar system, there are a large number of icy worlds, water-rich worlds, things from Pluto scale, slightly bigger, slightly smaller. Many of them may well have interior liquid oceans, which are a prime astrobiological target. And then my last little piece here, which is, again, something that we could probably start thinking about right now to do with interstellar exploration. And I noticed there was a question about would these star chips talk to each other and so on. Maybe they can't. But what do you want controlling your starship when it's 4 light years away from you? Now, you may not be able to do very much as a star chip. But I would like Chuck Yeager on that chip, or someone like that, or Neil Armstrong, or whoever, making decisions. There will be decisions to be made as a spacecraft. So what about autonomy at an extreme level with AI, or conceivably this magical, mythical thing of artificial general intelligence? And that gets me to the last piece, which is people talk about AI and AGI as existential threats potentially, right? Well, putting them on a ship going at 20% the speed of light into interstellar space has got to be the ultimate safe box if you want to do extreme AI experiments. Do it that way. They're not coming back, right? They may be really mad at you, but they're not coming back. Okay, so I'm sorry, some of that was a little frivolous, but I think there's huge potential for astrobiology from current real science to these more speculative ideas, and I'm very excited to see what's going on in the effort to bring space to more people. Thank you.
So can you measure really dark satellites with your LiDAR?
Well, I have to run the numbers. I mean, it literally came to me at about 11:30 last night, and I was too tired to run the numbers. I don't see why not.
So maybe it's already being done?
You mean by us or by someone else? Yeah, I don't know. But yeah, no, I think it makes sense. I mean, once you get up in the power regime of these laser arrays, it's a whole different ballgame what you can do with them as a sort of I call it active astronomy, right? You're pinging stuff in the solar system, and you're going to get enough photons back, and you've got this big array to detect them, just as you would the little chips around Proxima Centauri. So I think there's a whole bunch of interesting science you might be able to. So I have to run the numbers and see what is possible. Any other questions? Oh, sorry.
If you had 2 minutes with an investor, is that pocket sort of foundation? Or
I'm sorry?
if you had 2 minutes with an investor, someone out of cash burn, how would you talk to them about the benefits of this?
All of this?
Sure, something. I mean, I'm sold.
How would I do it? Oh, I don't know. I'd have to, I mean, this is a lengthy spiel, right? This is not the simple elevator pitch. I guess I would come back to say, look, there are still some profoundly important questions that we simply don't have answers for. And one of them is, are we alone in the universe? And the path to answering that question is going to involve the development of techniques and technologies that are going to profoundly impact our future. That would be my 2-second pitch. Yes?
So Warren mentioned that they have the breakthrough watch, breakthrough listen. Thinking about senses, like smelling life. Well, yeah, the next iteration of those projects. Is this something that you're involved in?
Smelling life?
Yes.
Yeah, no, I know what you mean. So yes, I am. So one of the projects we have here at Columbia, actually in collaboration with NASA, is building supercomputer models of Earth analog planets to look at things like their atmospheric chemical composition. Life dumps refuse into the atmosphere in the form of chemicals, some of which are simple like oxygen, but they're more complex biologically produced compounds that are absolutely, they're targets of the next generation of big telescopes looking for biosignatures. I mean, essentially, you're looking for the smell of life in a planetary atmosphere.
How can college students get more involved with astrobiology research? There's not a lot of astrobiology major programs. I know Princeton has a certificate program. But if students are really interested in this, what would you advise them to do to get in touch with researchers?
Well, that's a good question. I mean, so one thing just to say, I think part of the reason there aren't really any majors in astrobiology, that astrobiology is so broad that it would be very hard to design a course where you would drill deep enough to really get some strong basic science in the course of 3 or 4 years. So most people end up moving into astrobiology in graduate work where they begin to home in on a particular area. I mean, in terms of, for undergraduates, there are many programs. I mean, NASA's Astrobiology Institute is a big deal. It's in multiple places around the country. It also operates a large virtual sort of campus with online talks every week. If you sign up for that, it's a great resource. And they also do offer many opportunities for undergrads to at least to get together in conferences, to see what's going on, to interact with scientists doing this research, and also obviously to have the opportunity to work in labs and so on. It's still a field kind of finding its feet, actually, as is exoplanetary science. And part of what we want to do in the next few years is solidify that and make it easy for young people to walk right in and do the stuff that is most exciting for them. I mean, I have to tell you, teaching, if I teach cosmology, people get really excited, or black hole physics, people get really excited. If I teach astrobiology, people get really excited. Statistical mechanics, not so much, which is unfair, but the trick is to blend it all into, this is potent stuff.
Okay, so thank you very much.